This video discusses rates of change. So we're going to be looking at how things change, as we've already discussed before, right? The derivative basically tells us how a system is changing, and then we can then simulate that by performing numeric integration. So we're going to look at a few different systems today that either grow or decay or maybe a little bit of both. And so we'll look at growth and decay, charging and discharging, and also we'll discuss a predator and prey model. All right, so again, the derivative specifies how something changes. So if we look at, if we have some function p here, and that function is actually a function of time, and so if we see how it changes in time, so if it changes in time with a constant change, then we know if we integrate that, then we end up getting 5t, which is effectively the equation of a line. All right, so if we have the system changes at a rate of 5 per time unit, then it increases as time increases, it increases with the slope of 5. If it increases at a rate of t, so as t increases, the rate also increases, then we end up getting a parabolic t squared sort of form from that. Now, one of the most interesting is the fact that if the system changes at a proportional rate to itself, so if we have this function p, as in population, the reason they're using p here in the book is they're mainly talking about the population. It could be the population of bacteria, the population of people, or when we get to the predator prey, the population of a predator or a prey sort of thing. So that's kind of why they're using the p variable here. But if we look at the change in p, and it's proportional to the number of the population or whatever there. And so when we integrate that, we get something kind of interesting when you integrate that. You end up getting that the population then is equal to E times that coefficient to the T power. So you have this E. Now E is sometimes referred to as Euler's number. And so this is one of those natural constants, kind of like pi. It's considered an irrational number. Just kind of goes on and on. And so when you look at your scientific calculator, they actually have an E button there. And of course, the natural log is the reciprocal of the E. All right, but I think it's very interesting that when you look at some system that is changing with respect to the current value of that system, then this irrational value referred to as Euler's number pops up. So the first 5 digits of that is 2.7183. But this is one of those irrational numbers that we see popping up in nature all the time. All right, so if we want to look at the population specifically, pick any sort of population, but of course there's going to be births and deaths. So like when we were looking on this screen here, if this was actually a population, the population is just going to continue to grow and grow exponentially. It's just going to grow and grow and grow as fast as possible. But in reality, such a population growth can't be maintained, right? But so this is unconstrained growth. So the book uses the term unconstrained growth, where this is just going to grow, and as it gets bigger, it gets bigger faster and faster and faster. So it's unconstrained. There's nothing that's ever going to stop it, and it's just going to grow faster and faster. However, we know for, and, if this P really truly represents a population, then what's going to happen is, there's going to be a death somewhere along the way that is going to cancel out the amount of growth. So this shows us this equation here. If we have this variable rho here, it looks like a lowercase p, but it's actually technically rho. But if we look at rho times the population, that specifies the growth. So, whatever value rho is, the larger rho is, then the more births that you're going to have. So if you look at, for example, if you look at something like, people, typically they only have, one child at a time. Sometimes they might have twins or triplets, but most of the time, we as humans give birth to just one baby at a time. But on the other hand, if you look at something like rabbits or dogs or something like that, they may have 3, 4, 5, or even more at the same time. So that's kind of what this rho value refers to. And then over here we have a rho divided by a mortality value. So the capital M there is kind of like a mortality value, which specifies the death rate. Okay, and so the capital M again just kind of is a mortality rate. So if we kind of do a little bit of algebra on this, then we get that the population would be equal to 1 minus 1 minus M E, and I just noticed that's a kappa there. It should be a rho value there instead of a kappa. So this should actually be a rho. Yeah, I just noticed that. All right, so we get this 1 minus 1 to the mortality. All right, and so if the mortality rate is 1, then you end up, get a 1 minus 1, and your population is going to remain constant. Right? So if M is equal to 1, 1 minus 1 gives us 0, so your population is going to remain constant. Now, this isn't saying that there isn't births and deaths. It's saying that the amount of births is equal to the amount of deaths, and therefore the actual number, the population is not going to grow or decline, but be maintained at a constant value. So yeah, you do have, new births, you do have deaths occurring, but when M is equal to 1, then the overall amount of the population remains constant. All right, just some other examples here. If our population is like a quadratic, give you just an example here: t squared minus 6t plus 8. If this was kind of your population equation, right, then we could apply the quadratic equation, and we could find that at points 2 and 4. Now remember, this is the derivative, and when your derivative is equal to 0, you're at a local maximum or a local minimum, right? So at point 2 and 4, we're at either a max or a minimum. And if we take the second derivative then and evaluate at 2 or 4, we can therefore find out whether it's a minimum or a maximum, because it would be a positive or a negative. Okay. So, if we wanted to try to plot this is just the code here to plot this t squared minus 6t plus 8. And then there's the plot. So again, at 2, we can see that is a max value. All right. I'm just not saying it's the maximum that the population ever gets to, but it's a local maximum. So within this area, this is the maximum. So it's below, and then it reaches the max right here at 2. then it drops back off and reaches a local minimum at 4, and then it increases up again. Okay, so so this is just a graph for this. I'm just showing this is the code that we could use to actually plot this. Okay, so what we're doing here is we're evaluating the derivative. So we're evaluating the derivative. All right, so thanks for joining there. So we're evaluating the derivative, and then we're integrating. Okay, so here is our for loop, kind of like what we did before, but the difference that what we're doing with the Super Bowl example is that we knew the derivative for all time. All right, and so we knew the derivative ahead of time, and in the examples we've done before. But now what we're doing is inside of our for loop, we're going to find the next derivative. All right, so I have this program just as dp, but I could have actually made it like dp k plus 1, or excuse me, dpk, I guess, depending on how you laid it out. And then this would be dp of k minus 1 here. And so, but if I do that, I also have to initialize my dp ahead of time and set that equal to whatever growth rate that is. And I need to know what that is ahead of time. But and so we could do that. Okay. But what we're doing here is now we have our for loop, which we're going to integrate. But before we integrate, we're actually going to evaluate the derivative each time. And the reason that we do that is that we don't know what the rate of change is until we know what the current value are. So remember, like if the population is dependent on itself, as the population increases or decreases, it's going to change how fast the population is going to change. And now in this equation, the population isn't here, so that doesn't apply really. But just in general, most of the time in our for loop, we're going to have two sections. The one section is we're going to take the derivative, and so we're taking the derivative to find out the rate of change. Okay, so we're doing this to find the rate of change, and then we're going to integrate to find the next value. All right, so but we first have to figure out how fast is it changing, and then we do the integration. So we're going to evaluate the derivative, right? So that, I mean, we sort of know what the derivative, how the derivative responds, right? So this is the equation showing how the derivative responds, but we can't always evaluate it ahead of time like we were doing with the example of the car going to the Super Bowl. So now we have to evaluate as we're going, and we're going to evaluate the derivative to find out how fast it's changing. Now, once we know how fast it's changing, then we can calculate the next value. Okay, so that's kind of what's going on here. All right, and so again, that just is, here's the graph for that particular code. All right, but when we have the this is the Malthusian model for population growth, where it's basically saying that the population is proportional to the current population. All right, and so this has no limiting factor, so we're just kind of saying, you know, if you have a mother and a father, parents, and so then they have an offspring, and then as you have more offspring, then the population is going to grow more, right? So it's proportional to itself. All right, and we know the solution to that, right? I gave you that solution right here, right? So here's the Malthusian. We have the derivative is it proportional to some value kappa here times the population itself, and that gives us this e to the kappa times the time, right? And so we see this natural number e popping up here. So we know that's what the solution looks like, but what we're going to do is we're going to solve it numerically. So when we solve it numerically here, all we have, this is our derivatives, but again, we have to evaluate the derivative each time because it's changing each time. So we don't know the derivative ahead of time because we've got to work both the derivative and the next step in the integration simultaneously. All right. So here's just this is just kind of a generic example of what we have to do. All right. So the first thing that we're going to do is we're going to initialize our variables. So we come in here, we would set our t variable. Well, we'd set our time step. Okay. And I just normally, if I don't have an idea for time step ahead of time, I usually choose 0.01. But whatever your time step's going to be, then we're going to set this equal, and then we're going to go from our time step to however long that we want to run this. Okay. And then we have to initialize our value. Okay, so we have to kind of evaluate our we have to have initial conditions. So we got to know, like, what is our current population? So our current population, if our current population is 0, then we can never grow, right? So because you need some sort of parent to, even with bacteria or single cells that split, right? If you don't have any cells, they can't split in half to double or anything like that. So you got to have some sort of non-zero population in this case, whatever it might be, but you have to know that, but I mean, it's a population, so you just count it. There's, you go out and count the population. I've got, 6 of these or whatever, and then, as a, I don't know if you wanted to start raising rabbits or something, you go out and you buy 6 rabbits, so you know what your starting population is, something like that. And then then your derivative here, we can actually evaluate the derivative dp of k minus 1 then. Well, we have to, you could do this inside here. If you're going to do it, you're going to be 1 short when you plot, so you just need to keep track of that. But remember, this is just equal to that kappa variable times the population of k minus 1. And then now we can calculate then our next population. So our next population here at k is equal to our previous population plus the time step times this previous change. So how fast were we changing at that previous time step? Or actually, this is kind of actually at the time step now, and we're predicting the next time step. So this k is really predicting the next time step. So we're saying this is where we're at now. This is our current population. This is our time step, and this is how fast we're currently changing. And then this is where we're going to be in the future. So that's kind of what that's all saying there. All right. So, but I mean, this is just the example for population. But this original slide was just saying, you start out, you create your initial variables, okay, and so you create your time step, you create your time vector, you set your initial conditions. And then you go into your for loop. In your for loop, you evaluate the derivative. and then you integrate. And then once you have that, you've got your vectors and you can start plotting. So again, just one note here, dp in this example is one less than the dp's length is one less than the length of t. Okay, the way I did this in this example. This would work, but when you try to plot it, you remember you have to kind of just plot your t value. You know, so if you were to plot your derivative function here, you would plot t from 1 to n to minus 1 and then dp, okay, to plot your derivative piece, okay, because it's one less, but the population, the p-value is the same as your t. All right, so actually when the actual code, this for loop is not valid code that's written. It's from 2 colon to the length of t, which would make that valid. So the original idea of this slide was just laying out what the steps are in a more generic form. Okay, and your book also does it in a very generic form. They just kind of say, these are what you have to do, but they don't give you specific code for a specific programming tool. All right, so if the system reaches a steady value, so it, you know, as you integrate the system, after a while, the system may come to a fixed point and not change. If that's the case, then it's said to have reached equilibrium or a steady state value, which means that what that means is that your derivative is now 0 because the system isn't changing. Okay, it doesn't say that your system is 0. It says that your system is not changing. All right, the system, you know, you could have, you know, 1, or you could have 100, or you could have 1,000,000, or whatever. So you know, your system is a non-zero system, but once it reaches this equilibrium, it's not going to move unless some outside disturbance comes in to disturb it then. All right, so an outside disturbance now, when that acts on the system, okay, it can then make the system move again. So the derivative could go to 0 and the system will just sit right there and not move. But then when we get this outside force, now the system's going to move again. Okay. Now, if we control this outside force, we call it a forcing function. Okay. So if we can control the outside disturbance, we call that a forcing function, and we can force the system. All right. So when you look at the system, okay, if the system stays basically remains a finite value, then the system is said to be stable. If the system goes to infinity, if your simulation goes to infinity, then the system is said to be unstable. All right. Now, I don't know if I've ever discussed that before, but if we look in the software, in the Octave or MATLAB software here, you know, we know according to mathematicians, you cannot divide by 0. All right, but if you divide by 0, what you get, okay, you get a warning. Notice it's not an error, it's a warning, but you get a value, your value becomes infinity. All right, so let's just kind of take a look at that for a minute there. But if you take 1 divided by 10, of course you get 0.1. If you take 1 divided by 5, you get 0.2. Right? If you take 1 divided by 2, you get 0.5. If you take 1 and divide it by 1, of course you get 1. If you take 1 divided by 0.1, it grows. So you see how this is growing? So if we divide by 0.001, I get 1,000. If I divide by 0.0001, I get 10,000. And the number is growing and growing. So as I divide by a smaller number, I get a bigger number. And so in engineering terms, if you divide by 0, you can actually do that under certain circumstances, but your solution is infinity. Now, infinity means just a very big number. And so when you do something like this, again, I think most calculators, if you do a divide by 0, they just give you an error and say they can't do it. But in MATLAB and Octave, it'll actually let you do that. You can actually divide some value by 0, and it gives you a result called infinity. Okay, infinity just means it's a really huge number. All right, but if that's the case, then like if that's your value of your system, then that means it's unstable. That usually indicates that the system is unstable. One other thing though, sometimes you can, during your simulation, if you start getting infinity, the system may not be unstable, but maybe your time step is too big, okay? Or there's an error in your simulation, but the system itself is stable. So, if you start seeing that infinity pop up, or another value you see pop up a lot of times is NaN for not a number. Either one of those, if those start popping up in your simulation, then it's one of two things. Either you have an error in your equation somewhere as you're executing the code. A lot of times you got a negative sign wrong or something like that, and it's growing when it's supposed to be going down or something along those lines, or just that the system is unstable. Okay, or well, no, I say if the system is stable, if I know the system's stable, maybe your time step's just too big. So if you decrease your time step by probably quite a bit, that may also help. Okay. Again, remember the smaller you make your time step, the more executions it's going to require on your simulation. So it's going to take your simulation longer to execute. All right, one of the examples we're going to do this week is an example about modeling drugs within the human body. Okay, so and the human body is obviously a very complex system, and we have lots of parts, including our liver, right? And one of the things of the liver is to basically remove drugs or toxins, right? The purpose of the liver is to remove toxins out of your body before they destroy your cells. And so when we take drugs, even though they've been prescribed by the doctor, okay, I'm not talking about illegal drug usage here, but I'm talking about legal prescription drugs, or possibly over-the-counter drugs, but in this case, they're actually talking about a specific prescribed drug, right? But a lot of these drugs, even if they're, kind of recommended by the doctor to take them, if you take too many, they can be extremely dangerous, all right? But if you don't take enough, then it really does nothing. So when we start looking at drug reactions within the body, there's two values that they look at. One of them is referred to as the MEC, or the minimum effective concentration. So what they're saying is if you don't have at least this much of this particular drug in your body, it's not going to do you any good. It's just not enough in there to really affect your body, meaning that your liver is going to get rid of it before it really has any chance to help, address the issue that you took the drug to address. And then there's a second value called the MTC, the maximum therapeutic range, or the minimum toxic concentration, that you can, that if you take more than that, now you're starting to do more harm to your body than you are good. All right. And so there's a lot of drugs that are like this, that, I mean, most drugs really, right? You don't want to take too many of them. You don't want to take too much at one time, but you have to have enough in there to have a effect on the body. And so we have these two values here, the minimum effective concentration and the maximum therapeutic range. Now, the other thing we run into when we're trying to simulate drug dosages is that, you don't take a drug every second. If you're, like, let's just say something like aspirin or something, right? When you read the instructions on an aspirin bottle, they say take 2 of these right now, but don't take, wait 6 hours before you take any more, right? So they say, like, every 6 hours take these, or every 12 hours. Some of them are, rated for 12 hours. So they're saying take it only twice a day, once in the morning at 8 a.m. and once at night at 8 p.m. or whatever. So we got these pulses here. Now, again, these pulses are kind of like a forced disturbance because we're controlling that. But we have to generate a pulse. Okay, so the dosage is something that we're going to take, whether it's ingested or injected into the system, but it's a spike that happens just at periodic intervals. Boom. Okay, we just took another one. All right, and then for this dosage, we have the elimination, right? Like I say, the liver and is going to, your blood flows through the liver, and these toxins are then removed out of the bloodstream at a constant rate. All right, now that rate depends on a lot of different things in there, but so there's something they call the elimination constant. And so then there's the amount that is being removed, which is this eliminated constant, times the amount of drug in your body. Okay, and of course there's also other factors like, the weight, the mass of your body and things like that also can be included in this. But remember, we talked a couple weeks ago, one of the things that we want to always keep in mind is that the keep the simulation as simple as possible to at least start and get it so that it seems to be working, and then you can go in and add in more complexity, such as trying to determine, somebody who weighs 120 pounds compared to somebody who weighs 180 pounds compared to somebody who weighs, more or less in either direction. So this is the graph out of the book, or not a graph, but a kind of a diagram that he tries to show you in the book here. And sometimes it's a little hard to follow this diagram here, but he's kind of showing you that, okay, when you take the drug, all right, the dosage is like the drug. So if you get like, I don't know, an aspirin or something, and it's says, okay, here's this pill, and it's 100 milligrams of, whatever the fancy drug name for aspirin is. And so your dosage is 100 milligrams or whatever it is. But the fact is that you don't actually absorb all of that. Okay, some of it actually just goes right through your system and isn't actually absorbed into the blood to begin with. So it never actually makes it to the liver because it never made it into your bloodstream. So that's this absorption factor. So you have like the dosage times the absorption factor. And then there's also, how often are you taking it? Are you taking it once every 4 hours, once every 8 hours, once every 12 hours? Maybe you're only taking it once a day. All right. So those are kind of factors that get into the intake of the drug in your system. And then you have your elimination. Okay. What is that elimination constant? How fast is it being removed? All right. And as part of that is like the half-life of the drug. So, the drug may lose its potency after a while also. And so then the result then is, what is your concentration? So how much is in your body? And the concentration usually is based on also your mass, or volume piece here. So these are just all the different pieces that they're showing in this equation. All right. And again, this equation is in your book. This is figure 3.53 or figure 2.53 in the second edition of the book. So, and most of you probably have the second edition now. So it's figure 2.53. He renumbered the chapters a little bit. But so anyhow, the change in concentration then is equal to your dosage minus the elimination divided by the volume. So this is the equation that he gives us for the change in the concentration. So this is your derivative. Now notice here though, the dosage, right? A lot of times we're simulating this. We may be simulating this with a time step of 1 hour, or maybe we're simulating it with a time step of 1 second, but we're only taking the drug once every 8 hours or once every 24 hours or something like that. So the dosage piece that you're looking at here, the dosage is going to be 0 most of the time. So most of the time it's a negative, and your body is working on removing this drug out of your system. But then you take that dosage, you take the certain amount of the drug, and then it starts then there's a big spike. So that when you take that dosage, it's a positive value. So the amount of the drug in your system is going to spike positive, but then it's going to decrease then over time while the dosage is 0. So we need to look and see how to create this dosage. Okay. And again, something that we control is known as the forcing function. This there's a question in the homework right here. I think in engineering terms, a known external disturbance is referred to as a forcing function. So it's something that we're using to push this system along the way. So in this drug example here, we're taking it. So how do we do that? Well, there's a special function called the modulus function, okay? And it's actually just spelled mod in here, but you've probably heard modulus talked about before, right? The modulus is effectively the remainder of the value. So if you see here, I'm using a modulus of 3, means like I'm dividing by 3. And so 1 divided by 3 is 0 with a remainder of 1. 2 divided by 3 is 0 with a remainder of 2. 3 divided by 3 is 1 with a remainder of 0. 4 divided by 3 is 1 with a remainder of 1. 5 divided by 3 is 1 with a remainder of 2, and so on. So what we can do with this, using this code I show you here in the slide, is we can now then generate a pulse. Okay, and so we'll create a pulse that needs to be the same length as our time vector. And so we need to build up our time vector, and then we can build up our pulse vector. And again, they should be the exact same length. So let's just take a look here in the code. or all right, so if we create a time vector, say from 0 to, let me go 18. Okay, so here's my time vector. And now I'm going to create a pulse. I'm going to create a pulse which is equal to zeros the size of t. So now notice here, remember the whos command shows us the size. And so notice that t has 19 elements, right? Because it starts counting at 0, the step is a 1, and it ends at 18. So there's 19 values of t. So now I created a pulse vector. Okay, I called the vector pulse, but currently this pulse vector is all zeros, but there's 19 of them, so they exactly match my t. All right, but now I want to, let's say that I wanted to take a take this particular drug every 8 hours. Then what I need to do is I need to generate a pulse of 1. So what I'm going to do, if we look at this, right, if we look at the modulus, right, 0 divided by 8, 0 divided by 8, of course, is 0 with a remainder of 0, okay, because there's nothing there. 7 divided by 8 is 0. Well, 7 divided by 8 is 0 with a remainder of 1. Okay, I mean, if you do it here, it gives you fractions. But if you're looking at even number integers, right, it's going to be 0 with a remainder of 1. So if we look at the mod, if we do mod of 7 comma 8, the answer is 7, because it's basically looking at the remainder. But if we do the mod of 8 divided by 8, we get 0. So now I'm kind of losing my lines here, so let me just recall. There's t, and here's my pulse, which is all zeros. But now what I'm going to do is I'm going to say I'm going to get my mod 8. Mod 8 is equal to let's see, the mod 8 here, we're going to do the mod for my pulse. Okay, so I'm going to get these, oops. Okay, so we're going to take and we're going to do the mod of t divided by 8 of t comma 8, sorry, t comma 8. And so then what that's going to give me, okay, so there's my t, and here's my pulse. So let's try this one more time. So we're going to do mod of t comma 8 and then a parenthesis. So notice here it goes from 0 to 7, then it goes from 0 to 7, and then it goes from 0 to 7 or again, and again, and of course it just ended at 18, so that's why it stops there. But as you run it longer, it would go longer. So now I'm going to use that find command, and I'm going to say use in my pulse, okay, I'm going to find the values where mod 8 is equal to 0, which is going to be the first value, the 9th value. Remember, the 9th value is time at 8. Okay, and the 17th value is time there. All right, so we can just look at that before I execute it, right? So if I just do find mod A equal to 0, that's at 1, at 9, and it's 17 elements. And so what I'm going to do is at element 1, element 9, whichever one of these is element 9, and at element 17, I'm going to shove in a 1. So the way I do that is I can say pulse. So I can say now my pulse at these indexes. I mean, you can do it in one shot, or you can do it in multiple lines like I do on the slide there. You set that equal to 1. So now look here at the 1st, the 9th, and the 17th element. They're 1s, but the other values are all 0s. And so what I've done is I'm basically saying if my time step was 1 hour, and I wanted to generate a pulse every 8 hours to take this drug, then this would be my pulse. So then my dosage, okay, my dosage then is going to be 100 milligrams or whatever times my pulse. And so I'm getting my dosage of 100 milligrams every 8 hours. Okay, and so then if we tried to plot that, T comma dosage, okay, and we look at this graph, then you can see that at 0 and at 8 and at 16, I have a dosage of 100. And the rest of the time, there's nothing, right? Because I'm not taking the pill at those times. So that's how we can generate that's how we can generate a pulse for something like, taking drugs every 8 hours or something along those lines. So making use of this modulus function right here. Okay. So what we're doing is we're dividing by whatever value, and then we divide our t vector by that, and we get this reciprocating. I'm dividing by 8, so I'm going to end up with values 0 through 7. Then it's going to repeat 0 through 7, and then it's going to repeat 0 through 7 again and again and again. And then I'm just going to use the find command, find the values that are zeros, and use that to force 1s in my vector of all zeros. So I start with a pulse vector of nothing but zeros, and then I put in non-zeros at those points. Okay. All right, so another example I kind of wanted to do here is a kind of a growth rate. Is something that we do an awful lot, is like charging our cell phones or other portable devices. All right, and so when you look at that, basically the model of a cell phone battery is there's a constant voltage value in there due to the chemistry of the battery. So if it's a lithium ion cell, depending on the actual chemical makeup of the cell, it's maybe 3.7 to 3.8, 8.5 volts, 3.85 volts, something like that. And that's just, again, due to the chemistry of that battery. But then we charge it. So this here, up above here with the C, it represents what we refer to as a capacitor. And a capacitor is basically an electronic device that we can put charge into. So that's why we use this as a model for an electrochemical cell. And so the idea is that we are going to charge up this battery. Now, to charge up the battery, of course, we need an external power source. So a lot of times, right, we use our USB cord, which is actually outputting 5 volts. And we are going to connect that through some resistance, okay, into our battery. Now, the amount of current is the flow of charge, and the amount of current that's actually going to flow is based on what we call Ohm's law, which is the voltage across this resistor divided by the value of the resistance. And so that current is the flow of that charge that we're going to put into that battery. Okay. So if we look at this here, then the change in voltage across our battery is going to be the 5 volts, which is our supply, minus the current voltage of the battery divided by the resistance and the capacitance of that capacitor within that battery. Okay, so this specifies how the voltage is going to change. So the voltage of the cell, that really should kind of say cell there. So the change in the voltage across the cell across the cell is equal to the 5 volts minus the current value of the cell divided by the resistance times the capacitance, where the resistance is the resistance within all the wires and things connecting the 5 volt supply. And also there's internal resistance in the battery there also that it can be kind of included in that. And then times the capacitance of the battery. All right. And so, and now this RC, this product RC is actually referred to as the time constant. And it takes 5 time constants for something to reach like 99.9% of full charge. Okay. So if we assume that our battery, our cell phone actually starts out what we would consider dead, then, so there's no charge on the capacitor, all right, then all we would have is that nominal voltage of 3.8 volts or whatever. So here is the code that we would need in MATLAB. We would have to define the capacitance C, which is actually in farads. I think I showed that on a different slide there. The units for that is farads. Resistance is in units of ohms. The time step that I'm using, that I used for this was 0.1 seconds. And then the RC, this is just the product of R times C or C times R. And then I'm running this for 5 time constants. So remember I said RC is your time constant, and it takes 5 time constants to basically charge up a capacitor that's completely discharged. All right, so our initial voltage on the cell is here at 3.8, so it's just below 4. And then our for loop, we're going to evaluate dV dt, and then we're going to integrate adding to it. So remember, we're starting here I'm going to get a little arrow here so maybe you can follow this. Okay, so here is our initial condition. The voltage across the cell is 3.85 volts. So that's our initial condition. And then we're going to go into our for loop. We're going to find out how fast the voltage is changing, which is the 5 volts of the power supply minus the voltage of the cell at the present time divided by that time constant RC. So that's how fast the voltage is going to change. And then we're going to calculate what's the next voltage. Well, the next voltage is the current voltage plus the time step times that change that we had. and that's going to integrate that. So the blue line here is showing us the charge. So remember that it started out at 3.85 volts, and then we charged it up here to 5 volts. So we've charged it up to 5 volts, and it took, a little over 3 hours with the given numbers that we used for this simulation. And then also notice the red is the current. So when you first start charging your cell phone, you get a very high current. And as the cell phone gets charged up, as the charge of the cell phone increases, then the current actually decreases. So when you're almost charged up, so you see like after 2 hours here, the thing was almost fully charged, okay? And so therefore, you're adding very little to it, okay? So now when I plotted this, notice that I set my label here. I just called this generically, this was the amplitude. And then I used the legend. And in the legend, I actually put the units because I'm plotting voltage and current on the same graph. The blue is voltage, the red is current. However, the current was in milliamps, and to get it to look okay on the plot, I actually had to divide it by 5. Okay, so I show that in here. So the units of the red is milliamps divided by 5. And I did that so that I could fit them both on the same graph. Now, a lot of times you don't want to do that, but every once in a while you want to try to show two different values on the same graph that don't have the same sort of scaling. And so you kind of have to scale the plot so that they're both easily readable so you can see what's happening on both of them in there. And so that's what I'm doing here. So I'm actually plotting the voltage is just 1, 2, 3, 4, 5, 6 volts. But the current is actually milliamps divided by 5. So I've scaled the current so that it would look about on the same par as the voltage does. I do want to point out one other thing, which I put in red on this other slide here. Lithium-ion batteries, if you actually charge a lithium-ion battery up to 5 volts, which is what that slide was showing, it's a good chance of blowing up your battery long before you hit that 5 volts, okay? So you really don't want to do that. The voltage of a lithium-ion cell should never go above 4.4. And actually even, I recommend keeping it down to about 4.2, just because it'll extend the life of your cell tremendously if you do that. But if you let the voltage of your lithium-ion cell get above 4.4, you're definitely risking that cell overheating or exploding. Okay, so you don't actually want to, do not even try to charge your cell phone up to the full 5 volts. Okay. Now your cell phones and things, they have electronics built in them to tell it to stop charging once it's reached that, and they won't let it charge up to 5 volts because that is not a good thing. I'm sure you've heard some stories of lithium-ion batteries catching on fire in airplanes or things like that. But depending on the chemical makeup, especially but if you overcharge a lithium-ion battery, bad things could happen. And that's true for most batteries. If you overcharge them, definitely going to damage the battery, if not make it explode. So, be careful when you're doing that. But in this simulation, we are actually charging it all the way up to 5 volts. But again, it's only a simulation. It's not a real battery. So, all right, so that's pretty much it for today. We're just going to do that. Oh, I'm sorry. I guess I wanted to do one more. I forgot, is the predator and prey. I guess I don't even actually have that in the slides here. But There's in your book, he talks about the predator and prey model. And the idea of the predator and prey is that you have two populations. So this is back talking about populations. And you have one population, which is the predator. And of course, the predator is going to prey on the prey. And so if there's more prey around, then there would be more food. And you see this in a lot of different examples. The example I'm using here, I call it rabbits and foxes, right? So a fox, foxes, they like rabbit for dinner. And of course, the rabbits aren't too happy about that, but so they got them long legs so they can run away. So when you look at the equation for this, you have the fox population, okay, and you look at this equation here, these values. We're looking at how, you know, the U here is basically like the mortality rate. It's a negative value, so it's kind of the mortality rate for the fox. But it's basically saying, you know, the foxes are going to either die of old age or they're going to die of starvation because there's not enough rabbits to eat, one of the two. But, you know, there's nothing preying on the fox. And so this, you know, this U effectively represents the mortality rate. And then you have this P times Q. P times Q is the interaction between the rabbits and the foxes. Okay, so if the fox is out there walking around all day and he never sees a rabbit, he doesn't have a chance to catch the rabbit for dinner, so he's going to starve that day. And but when he sees one, when he sees the rabbit, now the rabbit, you know, rabbits are really fast and good at getting away. They've got them long legs and they can change directions really fast. So just because the fox sees the rabbit doesn't mean he's actually going to catch it. And so this portion of the equation here is representing, okay, I saw the rabbit, but he got away. And so you know, so like this V term here represents kind of how many, you know, how many rabbits I see out of how many I actually interact with and catch and how many get away kind of term. I'm sorry, that's actually for the rabbit. Well, that's true up here to some degree, but it's up here in the rabbits. The P represents the rabbits. So the rabbit has kind of two negatives. The one is the interaction with the foxes. So S is 0.5 right now. For this simulation, S is 0.5. So what this is saying is that the 50% of the time, the rabbit gets away. All right. And so, and the other 50% of the time, the rabbit doesn't get away, and so the population of the rabbit just went down. All right, so that's what this term is saying. This term here is saying more of a mortality rate for the rabbit. And so those are there. But you can see that, like, you see this predator-prey model for a lot of different things. Rabbit and foxes is just one example. But one other point I want to make about this simulation here is the fact that when you do this simulation here, you know, this is ignoring things like hawks or eagles or coyotes or something else that might eat the rabbit. Okay, so this is kind of a closed system here where it's just foxes and rabbits, but it's ignoring any other predators in here, and I guess you could say any other prey or whatever. And it also is basically assuming that the rabbits have all the food that they want also, so that they're they're not dying by starvation, things like that. But so this is kind of a closed system. You could then try to enhance it by saying, well, okay, this is fine and dandy, but what happens when the coyotes move into the county and start catching some of the rabbits? Then the overall population drops, and then that's going to affect the population of the foxes. All right, so anyhow, so if we run this simulation, then depending on what values you choose. So in this particular simulation, you see that we have some up and downs for the population of the fox and the population of the rabbits. Okay, and but then they reach a constant. So these actually reached a constant value. And so what that means is that without any coyotes or anything else in it, we have a constant population of foxes and a constant population of rabbits. All right. Now, I don't actually have a unit here. I don't know if this means like 1 million rabbits to 1,000 foxes, or 20 rabbits to 1 fox, or what. I didn't mark those units down in here, okay? But but this particular graph here is actually showing you that the population of the rabbits and the foxes in this example becomes steady. And so they just reach a steady state value, a constant value. And that constant value here is where those two meet. And we'll talk a little bit more about this plot. This plot is called a phase plot. We'll talk about that next week. Okay. But if you change some of these parameters, let me try this one here. I don't remember which one of these. A lot of these, I've got a lot of different simulations of this. Oh, that one's running a long time. All right, so in this example here, your population is stable, but constantly changing. So what's happening here is that you're starting off here with a lot of rabbits. The rabbits are in blue in this example. Okay, and again, the population is in thousands. So this means there's like up here at the top of this is first peak is above 5, so there's over 5,000 rabbits. And at that time, there's maybe, I don't know, 300 rabbits or 300 foxes or something. So 5,000 rabbits, 300 foxes. But see, there's lots and lots of rabbits. So there's lots of rabbits here, lots of food. And so there's so much food that the rabbits are getting all they want to eat. So none of them are starving to death, and they're having lots of little baby foxes. So as the population of the baby foxes grow, there's more and more foxes. And so there's more interaction between fox and rabbits, and rabbits are because there's more chances of the rabbits from getting caught because there's more foxes. They may be running from one fox and run right into the jaws of another. That the population of the rabbits starts dropping off dramatically. And so the population of the rabbits drop, and then it when the population of the rabbits really starts getting low down here below, say, 3,000 rabbits, then the foxes aren't having quite so much luck catching them because there's a lot less rabbits around. And so they're not catching them as much, and so the population of the foxes decrease. So this gives us this kind of alternating, pulsating sort of thing where the population grows until there's so many rabbits that it's really easy for the foxes to catch them, and then the population of the fox grows. and so on. So you can see there that this kind of up and down sort of thing. So it depends on those parameters in that equation, exactly what kind of solution that you get. Okay. But this is the predator and prey model. You also have to do one of these for your homework. So just wanted to at least discuss it a little bit, give it a try. We'll talk about it more next week. We'll analyze them in more detail.